Okay, this is A-level physics, AQA paper 1 from 2024. As per usual, I can't show the paper on screen because otherwise AQA will get the channel deleted like they almost did in the past. So links to the paper and mark scheme are in the description. 1.1, state the names of the 4 fundamental interactions. Well, what it means is forces. We know we have gravity and we have electromagnetism. Well, I was going to say you can say EM for short, but you can't, apparently, which I think is a bit mean, but whatever. We have the strong force and the weak force. Now, we can say that, that's fine, we'll get the mark. But if we're giving it the full names, then we should say weak and strong nuclear forces. There we go. 1.2, state the products of the decay of a free neutron. This is beta decay, essentially, beta minus decay, I should say. So you know you have a neutron turning into a proton plus an electron. But then, of course, we know we must have an anti-electron neutrino made as well. Charge, baryon number, and lepton number are all conserved. 1.3, explain which of the fundamental interactions responsible for the decay of a neutron. So again, it's beta minus decay, and this is the weak force, or weak interaction. How do we know that? Because there are leptons involved. Whenever there are leptons involved, it has to be the weak force. Nice start so far. 1.4. The forces between two moving electrons cause their paths to change. Explain using the concept of exchange particles when the electrons pass. This is quite an unusual question, actually, but if we were to draw the Feynman diagram for it, then we'd have an electron there, an electron there. They come near each other and then they repel each other. And the idea is that if we're talking about in the context or with the model of QED, quantum electrodynamics, what is it that causes them to repel? Well, it's the gauge boson, the exchange particle, and that will be a virtual photon. So we say exchange particle for EM, why can't we just say that, but I'm putting it here, is the virtual photon. This results in momentum change for both electrons, therefore paths change. Very weird concept, bit of niche information there, but yes, QED is all about, well, there's no such thing as a non-contact force, as it were. There has to be something that is going between particles that are experiencing electric fields or magnetic fields, and that's the virtual photon. That's the idea. Is it real? Probably not. Is anything real? Probably not, but let's not get too existential in question 1. Question 2, more particles. We have a pion and a neutron interacting, making a K plus meson and a sigma, 0. I can't remember what a sigma is off the top of my head, but that's okay. We don't need to. We can infer it in a minute. Oh, we're told it has a strangeness of -1. Cool. So if it has a strangeness of -1, it must have a strange quark in there. So actually, let's just figure out what it is right now. I don't know if it's going to be useful, but we might as well. So if we're talking about charge of a strange quark is, remember that a strange quark has a strangeness of -1 because they're strange, anti-strange is +1. So the charge of this is going to be -1/3, just like a down quark. But then if we want it to go to 0 charge, then we must have an up quark in there. So that's +2/3. And then we must have another -1/3. But it cannot be a strange quark, because otherwise that would mean that it's -2. So it's going to be this. It's going to be SUD, actually. Usually we write that as UDS. Okay, what are we being asked then? Oh man, so many boxes. So we've been asked, what are these? I'm going to see if I can do this a little bit easier. Okay, a pi plus meson. It's a pion, it's a meson. It's made of 2 quarks, therefore it cannot be a baryon. Baryons are made of 3 quarks, so therefore that is not going to be the case. A neutron is a baryon, so I'm going to put B there. K meson, again, it's a meson similar to a pion, it just has strangeness, so therefore that's not going to be one. And as we can see, the sigma is going to be a baryon. We're not told that it's a baryon, so can we infer that? Yes, we can, because of course, if we look at the baryon numbers for all of these, we have 0 plus 1 goes to 0 plus 1. And so therefore we can infer that it has to be a 1. So yes, it is a baryon. Okay, is it a hadron? Yes, all of these are hadrons because they are made of quarks. There's no leptons involved in this at all. No leptons at all. And then finally, meson, it's just going to be the opposite for the baryons. So there we go. 2.2, we've now changed it so we now have a pi minus and a k minus instead. So what conservation rule means that this can't happen? Well, let's have a look at charge first. -1 and 0 goes to -1 and 0. So that's okay. So that's not going to be what we're looking at. Baryons is just going to be the same. So that doesn't make sense either. So it looks like it's going to be strangeness. Let's have a look. A pi meson doesn't have any strangeness. It can't have any strange quarks in it. It's only kaons that do for mesons. So therefore it's going to be 0 and 0. And we said that this was a UDS, so it has a strangeness of -1. Well, we're told that right at the start, aren't we? But a K minus meson, well, if it's minus, then we know we have to have essentially -1/3 and -2/3 charge. And so we know we're going to have an anti-up quark in there to get that -2/3. You might be tempted to say that's a down quark, but it can't be, because we can't have a down quark because it must have strangeness. Kaons must have strangeness. So therefore it's going to be another strange quark. So that means that we have a strangeness of -1. So why can't this happen? There's two things we can say. Strong interaction, as there are only hadrons involved. And so we could say that strangeness must be conserved. But there's also another thing as well. In any interaction, even if strangeness didn't have to be conserved, any interaction, total strangeness can only change by 1. But you'd get the mark for just saying the first thing. 2.3, another interaction yet again. We have pi0 meson decaying into an electron plus a positron plus a photon. It's very unusual for us to write a photon in these things, but whatever. Because we always get photons released. Don't care. Compare the rest energies of the particles involved in this decay. Oh, okay. So we need our formula sheet for this. Okay, so it's on the second page of the formula sheet. So electron, that is how many mega electron volts? That's 0.510999 mega electron volts. It's going to be the same for the positron as well, because they're just antiparticles. Mass is going to be the same. And then our pi meson, it's a pi0. They're slightly different. I mean, it makes sense. So 134.972 mega electron volts. Okay. I mean, it says compare, so let's find the difference. Difference in rest energy is equal to 134. It's going to be a very small difference, of course. Take away 2 times that 0.510. We don't care about that because, of course, degrees of accuracy and all that. Funnily enough, the mark scheme doesn't actually expect us to do this, but we're going to have to do this in a minute anyway, so we might as well. So that's going to give us 133.95 mega electron volts. And of course, it's been turned into photon energy. 2.4, the decay of the neutral pion leads to the production of further gamma photons. Explain why. Well, that's because E minus and E plus made, and if there's one thing that you should know, you don't see positrons just out in the wild, not really anyway. Why? It's because as soon as they come across an electron, they annihilate. So that's what's happening here as well. E plus will annihilate when encountering E minus. It could be the same E minus that it's made, or it could be another one, we don't know. But this does result in 2 photons produced. 2.5. Standard model is a theory that classifies elementary particles. Evidence for the theory has been collected since 1950. Term standard models over 1973 suggest why progress in particle physics is slow. What a terrible question. It's because huge apparatus required to deduce nature of smaller particles or more short-lived particles. So CERN, there's a ridiculous amount of money that goes into CERN. And what have they found? Not really anything. Waste of money, if you ask me. But people don't like it when I say that. 3.1, we have a prism, and we have this. Oh, that's better. That's not going to be straight, is it? Yeah, that's not bad. And that's B. Okay, so we have a light ray that's going in like this, and then it's coming out like this. Okay. We've been asked to, yeah, complete the path of the ray. Okay. Oh, well, look at this, actually. It is going normal to block B. Therefore, the angle of refraction, in this case, from going from block B into air, is 90 degrees. Therefore, it must also be going towards it at 90 degrees as well. The angle of incidence must be 90 degrees. It's a bit of a cheeky question, that is. So there we go. That's nice and easy. And then all we have to do is join up these bad boys here. 3.2, deduce which prism has the greater refractive index. Okay, so let's draw our normals on here. So let's draw one there, and let's draw one there. Okay, so really the only thing we're concerned about is this here, what's happening between A and B. And what can we see happening? Well, if this is I and this is R, we could say theta 1, theta 2, we can see quite clearly that R is smaller than I. So that's what we're going to say. R is smaller than, or let's say I is larger than R. And you should know, just as a rule of thumb, that the angle is greater when the ray is traveling faster, as it were. So therefore, the light wants to get away from the normal. And so therefore, we can say that the refractive index of A is less than that of B. So there we go. Okay, 3.3. Block is used with a telescope. Block can be used to replace with a diffraction grating. Describe one non-astronomical application of a diffraction grating. Spectroscopy. We can split light into its constituent wavelengths. Mousecube doesn't say that word, but I guess, what a weird question. Spectroscopy, e.g., chemical analysis. Let's go with that. Oh, we are doing spectroscopy. Cool. Okay, so we have intensity against wavelength, and we can see peaks there. The light passes at normal incidence going through diffraction grating. Number of lines per meter of the grating is G. The first order diffraction is that. Okay, we're just being asked to calculate the lines per meter. So G equals lines per meter. I'm just going to say lines per meter. There we go. This is, of course, let's write down the equation first. So n lambda equals d sine theta, or the other way around. I can never remember which way around it is in the formula sheet. This d is essentially meters per line. And so it is the reciprocal. So I'll tell you what, we might as well, you can do it step by step, but I'm just going to do it all in one go. So I'm going to say that as d is equal to 1 over g, I'm just going to say, therefore, n lambda is equal to sine theta over g. So therefore, just swapping these over, we're going to say g is equal to sine theta divided by n lambda. Okay, so what does that end up being? Therefore, g is equal to sine of what? 28.2 divided by, what's the first order? Cool, so it's just 1 times. We can forget about that. And then lambda is, I'm going to say that's 380 nanometers. So I'm going to say just here 380 nanometers, and so you should know that's 3.8 times 10 to the minus 7, or you could put 380 times 10 to the minus 9. Doesn't matter too much, and that gives me a pretty standard number. Well, actually that's very, very small, but you know, this is important stuff. So we're saying 1.24, let's say, times 10 to the 6 lines per meter. 3.5, scientist wants to obtain accurate value for difference in wavelength between X and Y line. Oh, I hate wordy questions. Option 1, analyze the second order spectrum. Option 2, analyze the first order spectrum from a grating. Okay, actually, this is quite a good question. I like this. So let's get our equation again. So n lambda is equal to d sine theta. So option 1, we're saying that using 2 instead of 1. So n equals 1 to 2. Option 2, I wish they would have gone with option A and B, but whatever. Now we're going with 2g lines per meter, and so that means that d is going, d is halving, all right? So d is halving, and n is multiplying by 2. Okay, so we are ultimately measuring angles, and so let's say sine theta is equal to n lambda over d, but like we said, d is equal to 1 over g, so actually this just ends up being n lambda g. Okay, so in order to be as accurate as possible, so increased accuracy and lower uncertainty if theta is larger. So therefore we want theta to be as large as possible. So which one of these options is going to achieve that? Well, if D halves, then that means that G is actually going to double. Okay. So actually it seems like they both have the same effect. Theta is going to increase by the same amount if you increase from N1 to N2 and you double the lines per meter. So therefore, we can say resulting angles would be equal. That is not a good S. There we go. Angles. So you get the marks for that. Would you get all 3 marks? I'm not sure. No, you'd get 2 out of 3 marks for that. Why? And I can guarantee you that not many people would have got this 3rd mark. Well, if we think about different wavelengths going through diffraction grating, so we've got blue light going in and we have red light going in, and for the 0th order, they're the same. If we have blue light going in there, red light is going to diffract slightly more. And then if we go for the 2nd order, that difference in angles is going to be greater. So that's the issue here. And it's a very, very mean question. So, however, at larger orders, we could say rays may overlap. It's not going to happen because the grating is so small that they're going to be far apart. I think that's a stupid mark. I guarantee that like 1% of people would have got that, if that. Silly question. Not a silly question, just the silly 3rd mark there. Okay, we have deuterium and tritium. We're talking about fusion here. 6. So we got that. That's our deuterium. That's our tritium. Both hydrogen isotopes. And that's making helium-4 plus a neutron. The energy from this reaction is transferred to kinetic energy of the helium nucleus and the kinetic energy of the neutron. Fine. Assume the kinetic energies of the hydrogen nuclei are 0 before the reaction occurs. Fine. So we're just talking about the energy released. We're not worried about the mass energy going in or the mass energy coming out. Rest energy, that is. Okay, show the kinetic energy of the neutron represents approximately 80% of the total energy transferred. Right. This is due to momentum. Okay, so this is a question about momentum. Whenever it comes to things recoiling away from each other. And it's a very mean question because they haven't set it up like that at all. So vast majority of people would have gone, what? So this is to do with momentum and energy. And it's not that often that we are concerned with what's going on with both. Usually we're looking at just momentum in a situation or kinetic energy. But in this case, we're looking at both. So we need an equation that links the two together. Now, this is in your formula sheet. And this is coming up more and more often these days, actually, over the past couple of years. They seem to be liking this. And so I think that this equation should be in the main part of the formula sheet, but it's not. It's actually in the turning point section because, again, this comes up a lot in the turning points module. But let's have a look at this. So we have a kinetic energy. I'm just going to put E is equal to half mv squared. But then what I'm going to do is multiply both sides by m. So we have m squared v squared. And so we can see mv squared, that's the same as... I'm just going to put that first. That's equal to half times momentum squared. I'm going to put P for momentum. Rearranging this, we find that P is equal to the square root of 2 times the mass times the kinetic energy. And therefore, well, we're worried about the kinetic energy here. So I'm going to rearrange this. We're going to say E is equal to P squared over 2M. Okay, so we know that if they have the same momentum because they're recoiling away from each other because the hydrogen nuclei are coming together, and then what is produced from that, they must have the same momentum. So therefore we can say that kinetic energy is going to be proportional to just 1 over m because P is constant and 2 is a constant as well. So if this is the case, then we can say that the energy of the neutron times the mass of the neutron is going to be the same as the energy of the helium times the mass of the helium. Fair enough. And so therefore, well, we're looking for, let's just say that the energy of the neutron divided by the energy of the helium nucleus is going to be the opposite for those. And so that gives us, well, that's equal to 4 divided by 1 if we're just looking at the mass of 4 compared to 1. And so that means that the energy of the neutron, or Ke of neutron, is 4 times that of helium. Therefore, total energy is split 4 to 1. So therefore, the energy of the neutron is going to be 4/5. That's 4 lots of kinetic energy divided by the total of 5. And so that's going to be 80%. Not a super easy question, again, because they didn't really set it up properly, but be ready for this. Whenever it comes to recoil of particles, you always think, right, they have the same momentum. Start off with that. And then don't forget how to derive this. It's useful. Sometimes they do ask you to derive it. So yes, you can look it up in the formula sheet, but it's also useful to know how to derive it. 4.2, combined kinetic energy of the helium nucleus and the neutron is that. Okay. Okay, so total kinetic energy is 2.82 times 10 to the minus 12 joules. So therefore, the energy of the neutron is going to be 80% of that. So I'm just going to say times by 0.8. Don't think I need to do the standard Fermi bit. And that gives us 2.256 times 10 to the minus 12 joules. And of course, we know that's equal to half mv squared. So therefore, I'm going to put that. V is equal to the square root of 2e over m. So that's equal to the square root of 2 times 2.256 times 10 to the minus 12 divided by the mass of a neutron. So it should be 1.67 times 10 to the minus 27. Let's tidy up some powers of 10. I'm just going to pop that up on top and call that 15. Doesn't make a big difference in the end, but whatever. And I end up with a very fast, some would say too fast. No, not too fast, actually. It's very fast, but not too fast. 5.2 times 10 to the 7 meters per second. I thought it was faster than the speed of light for a second, but it's not. Okay, we have a pole, and we have that. A figure 4 is a force diagram drawn to scale. No! What's the point in physics if we're just going to do scale drawings? That's just maths then. You know, I know physics is maths, but it's just, what's the point in building models and equations if you're just going to then go, oh yeah, let's draw a pretty picture instead. Complete the force diagram. What are we being asked? Go on to determine using your diagram. Oh my days, are you kidding me? Look, we need the, what's the word I'm looking for? Components. We're looking for the components, all right? I haven't done the first thing, which I probably should have done first. Ironic, I know. What we should do is we should move this vector over to here, and so it's going to look like that. Oh man, I'm doing a bad job. It's going to be like that. And then we're going to move this one over here. Okay, so this then gives us the resultant of both of these from start to finish there. So that's that. You'll get a mark for that. You can actually... okay, we could measure angles as well, and then we could use trig to sort everything out. That's the way I would do it. So there's theta 1. Am I going to go with that? Yeah, let's go with that. There's theta 2. There we go. So what are we going to do? Well, we're going to say that this is going to be, well, this is T1, this is T2. And so this horizontal component is going to be T1 cos theta 1. This is going to be T2 cos theta 2. And then the upwards ones are going to be the opposite. So T1 sine theta 1, T2 sine theta 2. If you don't know where I'm getting my sine and cos from, have a look at my easy vectors trick video. We turn through the angle to get cos, turn away, we use sine, and we want components. So therefore we're multiplying, not dividing by those. Okay, so we know that the upwards ones have to together equal 350 newtons downwards. So therefore we can say our first equation, so therefore T1 sine theta 1 plus T2 sine theta 2 is equal to 350 newtons. Fine. And then our second equation is going to be T1 cos theta 1 is equal to T2 cos theta 2 because the horizontal components have to be balanced too. So there we go. We have simultaneous equations. So therefore, we just have to then pop one equation into the other. So therefore, I'm going to rearrange this. I'm going to say that T1 is equal to T2 cos theta 2 over cos theta 1. Then I'm going to pop that into here. And so therefore, rearranging this, we end up with T2 cos theta 2 times sine theta 1. I'm just combining it there. Divided by cos theta 1 plus T2 sine theta 2. And it's up to you whether you do the find a value for the sines and the coses first. it does maybe slightly make it slightly easier, slightly. And then we factorize this, don't we? So T2, and that's going to be cos theta 2 sine theta 1 divided by cos theta 1 plus sine theta 2 is equal to 350. And then all we have to do is just pop all of this under here, divide by that in order to get our answer for T2. So we're going to say that theta 1 is going to be 35 degrees, and then theta 2 is going to be 12 degrees. So let's try putting this all in. I'm going to do the brackets first. So I'm going to say cos of 12 times sine of 35 divided by cos of 35. There we go. Then add on, oh dear, is that right? I made a mistake here. Let's find out. Plus sine of 12. Looks okay, actually. No, it's fine. And then I'm going to say 350 divided by all of that, and I end up with a T2 of 392 newtons. That looks pretty good, actually. Yeah, not bad. And so therefore now we can pop that back into just our equation 2. So we can say T1 is equal to T2 cos theta 2, where I'm just using equation 2 from up here, divided by cos theta 1. So that is equal to 392 times cos of, 12, divided by cos of 35. It's very unusual to have a question that just says, go on, find out the values for all of these. And I always taught my students when I taught A-level in school to do this, and it never came up. And so sadly, this was a year that I was gone. So no, technically I did teach them in year 12 how to do this. So I hope they did all right with that. So there we go. Not an easy question, just because, again, they don't hold your hand. It's just go on, find it. You need to infer that. You need to be saying that, first of all, the vertical forces are balanced. So the upwards components added together must equal that 350 newtons. And then the horizontal components are equal to each other as well. Fun times. 5.2, we're now releasing it from A. P and I move along the cable to B. Oh man, the change in height of the center of mass between A and B. Okay, so I'm going to say delta H is 4.5. And if you know my videos, you'll know I have a whole video that just says the theme is just, if you're given a height, it's going to be a question about energy. Simple as. The distance traveled along the cable is 18 meters. Yeah, this is going to be work done and GPE, methinks. The speed when it reaches B, yeah, there we go. So V is equal to 6.5 meters per second. And sure enough, calculate the average resistive force. So we're going to be using E is equal to mgh, and we're going to be using E equals FD. And third one as well, half mv squared. We know that the loss in GPE, so EGPE lost, is equal to EK gained plus work against friction. Again, that's just energy, isn't it? Cool. So we're looking for this. We know that this is going to be, well, let's say this work is equal to EGP minus EK. That's fine. We'll sort out the work bit in a minute, but that's going to be mgh minus half mv squared. So that's going to be equal to, oh, what's the mass? Oh, we've got the weight, haven't we? For goodness sake. So mass is equal to that 350 newtons divided by 9.8. And it gives me 30, let's go with 35.7 kilograms. Okay, I can factorize this. So I can say that's mgh minus half v squared. Not that it's that important, but whatever. 35.7 times 9.8 times, what was the change in height? 4.5 minus half 6.5 squared. Okay, so I'm going to do the middle bit first, I think. So 9.8 times 4.5, take away 0.5 times 6.5 squared, and then that's times by 35.7. So I get a difference in energy between the GPE lost and the KE gained of 820 joules. And so that's going to be equal to FD because of this work done. We can call it E, or W is equal to FD. So therefore D is equal to just, oh no, we're not looking for D, did I? So therefore F is equal to this energy, this work done divided by the distance. So it's 820 divided by, what's the distance? 18. And that gives me an average resistive force of 46 newtons. 5.3, O contains a fragile item packed in a suitable material. Material? Oh my days, it's been a long summer. Explain how the material can prevent damage to the fragile item when O stops suddenly at B. Well, just like our crumple zones in our cars, blah, 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 blah. All momentum is lost, but as F is equal to rate of change of momentum, that's delta mv divided by T, cushioning results in momentum lost over longer collision time. Therefore, F is reduced. Easy peasy. 6.1, so we have a thermistor and then a variable resistor. And we have our points X, Y, and Z. Initial temperature of the thermistor is 22 degrees. That's fine. I don't think we care about that, no, because it's just they have to tell us that. It might change in a bit, but we can't use a temperature for anything, so we don't care about the 22 degrees for now. At this temperature, the resistance of the thermistor, okay, so R of the thermistor is equal to 350 ohms. Why am I doing that? Well, let's put it there. And the current circuit current rather, is 12 milliamps. Oh, I should really be color coding my things. I'll try to color code to be consistent. So that's 350 ohms. I always use green for current for some reason. I don't know. Current goes, green go. I don't know. What are we being asked? To calculate the resistance of the variable resistor. We have an EMF of 6 volts. Sorry, 6.5 volts. Cool. So therefore, we just want to find out, first of all, the PD across the thermistor. And so therefore, we can say the V of the thermistor is equal to IR. So that's just going to be 12 milliamps. So that's 12 times 10 to the minus 3, or 0.012. And then that's going to be multiplied by 350. Easy. And that gives us 4.2 volts. So if that's 4.2 volts, there is a shortcut here, of course. We could just use ratios. We could do that. I'll show you how to do that in a second. So therefore, if that's 4.2 volts, then the PD across the variable resistor has to be 6.5. Take away that, so it's going to be 2.3 volts. And so therefore, it's the same current flowing through that. Therefore, Therefore, R of the resistor is going to be equal to, well, Ohm's law, V over I. That's just going to be 2.3 divided by, let's write that down, V divided by I. 2.3 divided by 0.012, or 12 times 10 to the minus whatever. So 2.3 divided by 0.012, and it gives us 192 ohms. The other way of doing it, of course, would be to find out the total resistance of the circuit using 12 milliamps and 6.5 volts, and then just take one away from the other. We could have done that as well. So 2 ways to skin that cat. Ooh, looks like we are going to be concerned with temperature right now. Okay, what are we being asked? So we have R is equal to, so the resistance of the thermistor is equal to the initial resistance times e to the, my word, B 1 over theta minus 1 over theta 0. Okay, so that's just the initial temperature as well. Okay. Whew. What are we being asked then? B is a constant, that's fine. Oh, determine B. Easy. Okay. So let's rearrange this. So let's do R over R0. For starters, this is an exponential equation, so you should be used to doing this when it comes to nuclear and capacitors. So that's equal to E to the B whatever. And so therefore, we're going to log both sides. So we're going to say log of natural log, of course, but I can say natural log because it is a log, just like any other log. It's just a base here, it doesn't matter. I'm not going to call it ln like an absolute weirdo. And it's going to be B 1 over that. So therefore, all we have to do then is just put that under there. So therefore, B is equal to, I'm not a weirdo, there we go, ln. So that's equal to log of, what are we talking? What was the new resistance? Oh no, we're going to have to calculate it, you jerk. Oh, that's okay. That's fine. So I need to, there we go. So the resistance, the new resistance of the thermistor is going to be, what was it? Nope, 3.2 volts divided by, again, that's 0.012. Fine. Okay, so that gives us a resistance of the thermistor at 267 ohms. Okay, so now we just have to pop everything in. So B is equal to log of, that's 192 divided by log of 267 divided by 350 divided by 1 over, what's our new temperature? Oh, I didn't look at it. 318 Kelvin. Minus 1 over, we need to get the initial temperature in degrees actually as well. So theta 0 is going to be that 22 degrees that we had, degree C, plus 273. So that gives us 295 Kelvin. So converting that to Kelvin, 295. Cool. And pop that all in. It's up to you whether or not you do that in a few steps or all at once. That gives us 1,000. Let's round it to, well, even 3 sig figs. There we go. We don't need the unit for that. That's our constant. Oh no, it says write an appropriate unit. Right. So if you know anything about, these exponential decay equations, you must know that together cannot have a unit. So therefore, if we have Kelvin on the bottom there, then that means the unit of this is Kelvin to the minus 1. So that means the unit of B has to be Kelvin in order to cancel them out. Weird. 6.3, explain why the current in the temperature needs to be controlled because otherwise higher current or changing current, whatever, will result in lower resistance. We only want ambient temperature to affect resistance. There we go. 6.4, explain how ammeters and voltmeters can be used in the circuit to demonstrate the conservation of charge and the conservation of energy. What? Why? Okay, well, dumb question. So if you put a voltmeter, all we need to say is that we can put a voltmeter there, we can put a voltmeter there, and we can put a voltmeter across the whole thing to show that. That's fine. Like, voltmeters across X and Y, some V's to give same V across X and Z. And that is your terminal PD. And also ammeters at all points will give same current. And we can say that, so as Q is constant, or rate of change of Q is constant, therefore V is equal to E over Q, therefore E is equal to VQ or QV is same, therefore E equals VQ summed for individual components equals energy dissipated in circuit. I don't know, it's a stupid question. Dissipated, whatever, I can't spell. Silly question. Next. 7.1, experiment, stationary waves, string of length, 1.05 meters. Stationary wave is formed on the string. Right. But it's not the first harmonic, looking at the diagram. So I'm going to say the third harmonic. So F3 is equal to 625 hertz. Okay. What are we going to ask them? Stationary wave is produced by two progressive waves. Of course, deduce the amplitude of one of these progressive waves. Well, you should know that at this point, if we're showing the maximum displacement, which is like this, then this is when there's total constructive interference, and that is a result of the two waves like so adding up to this super wave. So therefore, amplitude of one wave, or of progressive waves, of each progressive wave, there we go, equals half amplitude of stationary wave. Makes sense. They add up to that, don't they? That's what interference is. Or superpositioning. So the amplitude of the stationary wave is equal to 7 mil. Therefore, amplitude of progressive wave is equal to 3.5 mil. Easy peasy so far. 7.2. Determine in meters per second the speed of the wave of one of the progressive waves. Okay, so we have the wavelength is, looks like it's 0.7, so that's fine. So 0.7 meters, cool. And yeah, that's fine. We can just use V equals F lambda. Easy peasy. We don't care that it's the third harmonic. Doesn't matter. We have a frequency. We have a wavelength. That's all we need. So 65 times by 0.7. Should be able to do that in my head, but I'm not gonna. There we go. 7.3. Determine the phase relationship between the two waves when t equals 0. Oh, they're in phase. The doi, because they're constructively interfering, then they must be in phase. That's the whole point. Oh, I cannot spell today. Interfering. There we go. It's the easiest waves question of all time so far. 7.4. How does the displacement of S vary? Oh, okay. This is rather funky. How does it change with T? Okay, so there's our displacement up there. So let's see if I can get this right. So 0.5, 1, 1.5, 2 milliseconds. So that's time there. Okay. So how does it vary with time? Right. Well, we need the time period, don't we? So we can say that the time period is equal to 1 over f. So that's 1 divided by 625. And that should give us something in milliseconds, which sounds about right for what we're doing here. So that is 1.6 times 10 to the minus 3 seconds, or in other words, 1.6 milliseconds. Cool. So let's have a look. Well, we are at time t here. Oh man, I need to look at the diagram again. That is at time t. Okay, so S on, because we've got a point S on this graph up here. So S is at a displacement of 4 millimeters. Okay, cool. So at time 0, point S is at 4 millimeters. So wait, what does this graph go to? Yeah, same. So there we go. So that's 2, 4, 6, 8. Minus 2, minus 4, minus 6, minus 8, whatever. Okay, so it starts off. You got to remember that the initial graph is distance on the x-axis. This is time, and we're just looking at 1 point on the wave now. And so we're just thinking about this 1 point on the wave going up and down. It's not moving left and right or anything like that. We're just focusing in, laser focusing on this 1 point. So at time t, it's at a displacement of 4. That makes sense. And what do we know? Well, if it's at the maximum amplitude, then that is not going to change, because we know that on a standing wave, stationary wave, I'm just going to draw the flipped version of this as well. This point here is just going to go between here and here. This point at the antinode is going to go between here and there. And so all of these points, they have their own individual amplitudes. And so therefore, it's not going to go higher than 4 millimeters. The antinode will, but not point S. So what do we know? By the time it comes back to 1.6 milliseconds, which is there, then we know it must be back at 4 millimeters. And therefore, we know that 0.8 milliseconds, half that, halfway through its cycle, it should be down here. And so there's 0.4 and there's 1.2. So it's going to be something like this. And do we have to go more than that? Let's go another 0.4. Why not? So another 0.4 has gone through another quarter of a cycle. So it's just going to go off. It's going to go down like that again. There we go. It's quite a nice waves question there, wasn't it? Didn't even have to use any fundamental first harmonic equation-y stuff. Right, multiple choice. Love it. Question 8. Which nuclear change results in the nucleus with the greatest specific charge? Okay, specific charge is charge to mass ratio. And so therefore, what? It results in the nucleus with the greatest specific charge. This is I'm sorry, AQA, this is ridiculous. You're putting 3 questions in one here. That's so stupid. Why don't you just give us the nuclei? That's so dumb. So alpha decay of polonium nucleus. So that's going to end up being, I don't know what it's called, but it's going to be 205. and 80. And so that's going to be 80 divided by 205. If we're just talking about charge divided by mass. B is going to be beta minus decay of magnesium nucleus. So that ends up being then 28 and 13. So that's going to be 13 divided by 28. And then we're going to have C, beta plus decay. So that's going to be 39. But then we've got a proton turning into a neutron. So this ends up going down one. So that ends up being that. So it's 19 divided by 39. And then finally, electron capture. Electron capture is in essence the same thing as beta plus decay. It ends up with the same thing happening, essentially. And so that's going to be 105 and, whoops, I don't want that. 105 and 46. So that's 46 divided by 105. Great. So we're going to have to, what are we looking for? The greatest specific charge. Am I going to have to do all of these? Yeah, I think I am. Okay, 80 divided by 205, 13 divided by 28, it's not that one, 19 divided by 39, 0.48, so it's not going to be B, and then finally 46 divided by 105. I don't think that's going to give us, no, it's not. So, whoopsie, 0.43, so it's not that. So it looks like our answer is C. Good grief. Okay, photoelectric effect question, graph rather. Which graph shows how the maximum kinetic energy... Oh, okay, hang on a minute. The work function of X is greater than the work function of Y. Okay, for starters, we know that they must have the same gradient because, of course, the gradient is equal to Planck's constant. That is a universal constant that cannot change. So it cannot be B and it cannot be D because they have different gradients. Can't be that. Okay, so what they've done is that they've purposefully left off the minus bit of the graph to not catch us out, just so you have to think about that. And so therefore we know that if we have two graphs like this where the work function is different, we know that this one here has the greater work function because the energy tax, as it were, to get the electrons liberated so they can actually have some kinetic energy and escape, that's greater. So we can have the greater work function there. And so what are we told? The work function of X is greater than the work function of Y. Therefore, this has to be X. This has to be Y. So it looks like our answer is A. Okay, monochromatic light, photoelectric current I, maximum, yeah. The frequency of the light is increased. Okay, so if frequency of the light increases, what does that mean, first of all? Therefore, kinetic, and let's put it this way, the energy of the photons increases. So there's more energy available. Therefore, that means the kinetic energy max. Cool. So we know it can't be C or D then because we know that EK max is going to increase. But how is the current going to change? Oh, hang on a minute. I haven't read the whole question here. There is no change to the rate at which energy is incident on the surface. Well, that's a bit silly, isn't it? Because that would mean that you'd have to know that's... Yeah, that's not a thing. That's not a thing. But we're going to pretend that it is here. So therefore, if energy is the same, if total energy is the same, but energy of each photon is increased, it's good right of me, therefore fewer photons incident. Simple as that. Therefore fewer electrons liberated. Again, in practice, it's not really a thing. They're just trying to test you on this. There is the effect of the higher the frequency, the more likely they are to increase. The electrons are going to be liberated, but it's not going to completely negate the fact that there's actually fewer photons going to be incident. So therefore, the answer, again, looks like it's going to be A. Question 11, we have energy levels. Fine. So 21 electron volts. 6 electron volts. Again, do I care about the minus? Not really, because we're only ever looking at differences between these energy levels. Okay, what are we being asked? Energy change 1 leads to the emission of photon. Okay, what is lambda 1 divided by lambda 2? Well, I always say that whenever you have a question that asks you what is a ratio of two things that are the same, you just want to replace what they are proportional to. And so therefore we can say energy is equal to HF, yes, but that's also equal to HC over lambda. And so therefore we can say that energy is inversely proportional to lambda. Therefore E1 lambda 1 is equal to E2 lambda 2. So therefore the ratio of energies, or let's put it the other way around, the ratio of wavelengths is going to be equal to the opposite ratio of their energies. Simple as that. So it's just going to be 15 divided by 5 ends up being 3. So our answer is C. What was I just talking about? There we go. De Broglie wavelength of electron versus proton. So I'm going to say lambda E over lambda P. So what's our equation for de Broglie wavelength? Then it's going to be lambda is equal to H over mv. But they have the same speed, so therefore we can say that lambda is inversely proportional to m. So once again, we're going to say that you can go around the houses if you want to. You can say that equals that. But essentially, it just ends up being the opposite like we saw above in the previous question. So it's going to be the mass of the proton divided by the mass of the electron. So that is going to be 1.67 times 10 to the minus 27 divided by 9.1 times 10 to the minus 31. So let's just pop that on top and just say that's 4. That's 1.67 times 10 to the 4 divided by 9.1. And it gives us 1,835. So our answer is D. 13. Laser emits light of wavelength 600 nanometers. So I'm going to say that's that many meters for 10 nanoseconds. So 10 times 10 to the minus 9 seconds, or 1 times 10 to the minus 8 seconds. What's the number of complete waves emitted by the laser? Okay, so basically we need to know how long it takes for one wave to be produced. So we need the time period. That's equal to 1 over the frequency. How are we going to find the frequency? Well, F is equal to, because V equals F lambda, we know that F is equal to V over lambda, or C over lambda in this case, because it's the speed of light. So therefore the time period is going to be equal to 1 over F, or we could just say it's the reciprocal of V over lambda. So it's lambda over V, or lambda over C in this case, like I said. So it's going to be 6 times 10 to the minus 7 divided by 3 times 10 to the 8. I don't think we need a calculator for that. That's going to give us 2 times 10 to the 15, minus 15 rather, seconds. Okay, and then basically I'm going to put seconds per wave. It's always a good thing to do, make up your own units in these kind of questions that ask you, how many things do you have? How many waves? How many electrons? How many photons? Say I have this many seconds per wave. So we have seconds per wave. We're looking for number of waves. So therefore we're going to divide by this here. So we're going to do number of waves is equal to 1 times 10 to the minus 8 seconds divided by 2 times 10 to the minus 15 seconds per wave. They cancel, waves ends up on top. There we go. And we end up with 0.5 times 10 to the 7, it looks like. So it should be 5 times 10 to the 6. Do we have that? Yes, we do. It's D. 14. Detector measures the intensity of light. When the material is rotated through a small angle, the detected intensity does not change. Right, so that must mean that S1 emits unpolarized light, because if it's always half the light going through the filter, then obviously that means that it's unpolarized. And then S2, if it's repeated, then it must be polarized light if it is actually changing. So if it's vertically polarized, then it's going to let it through, but then not when you twist it through 90 degrees or vice versa. So which is correct? It's just going to be unpolarized and polarized, so it's going to be A. Easy. 15, loudspeaker, water. We're probably going to be changing what's going on here, the distances. Student observes the change in loudness of the sound emitted by the tube. Okay, when the length of the column of air in the tube reaches L1, the loudness is at its maximum. Right. The next maximum is reached when the length of the column of air is that. Okay, so if we just go for what it could be, it might not be this, but well, actually it kind of has to be, but whatever. So this is L1 and this is L2. And so therefore, we know it has to be an antinode there. And so therefore, it has to be a node at a closed end. So when the water's there, then it has to be a node there. So therefore, it has to be like that. There we go. So therefore, the difference between L1 and N2 is going to be half a wavelength. I probably should have done one of these in a dotted line. Let's do that. There we go. Doesn't really matter, but you can see it more clearly then. Okay, what is the wavelength of the sound emitted by the loudspeaker? There we go. So like we said, L2 minus L1 is equal to half a wavelength. Therefore, lambda is equal to 2 lots of L2 minus L1. So our answer is D. 16, Young's double slit, but with sound sources instead. Okay, sound detector has moved slowly along PQ. Classic question. Consecutive maxima of sound intensities at W and Y and minima at X and Z. Oh man, why do they? Okay, whatever. What is the wavelength of the sound? Well, what's interesting is that okay, right. No, they are doing it right. So it's all about path difference, isn't it? So path difference between two consecutive maxima or minima is going to be equal to one wavelength. Okay, so we're looking for the difference in path differences. Yes, that's what we're looking for, isn't it? Yeah, so the difference in path differences. So the same goes as well. Difference in path differences. Cool. So they all are path differences, so that's fine. So it's a little bit silly that they've given it in this form. But let's look at the first one. So S1Y minus S2Y, Y to W. Yeah, that looks right, doesn't it? Because A is, let's write it out. So this is the path difference for max at Y. This is the path difference, I can't write, sorry, at W. And therefore they have to be one wavelength apart. So that makes sense. Yeah, easy. Why can't it be, say, B? That's X to W again. Oh, I see. That's what they've done. All they've done for the rest of them is given us differences that aren't between two maxima and two minima. It's between a maximum and another minimum. So there we go. 17, Young's double slits. Resulting fringe pattern is observed. Separation of fringes. Okay, so we're going to need the equation. W equals lambda D over S. Okay, we want W to go up. So therefore A, using monochromatic light of lower frequency. So if F goes down, that means that wavelength goes up. So therefore, yes, that is correct. So it looks like our answer is A again. Let's see, why can't it be B? Decreasing the width of the single slit, that doesn't change anything. Really. Not really. No, it doesn't. Not with monochromatic light anyway, certainly. That's just going to change how much light gets to the double slit. Increasing the separation of the double slits. If you increase that, we can see that that goes up. That will go down, so it can't be that either. And then finally for D, decreasing the distance. That's decreasing big D. So therefore W is going to decrease as well. 18, mass on a slope. Love a good mass on a slope. Can I get that straight? Yeah, kind of. Okay, we have alpha and we have beta. Okay, what is the magnitude of the acceleration of the block along the slope? Okay, so first things first, we write down straight away mg sine. It would be usually theta, but we're going to go with alpha this time. And because we have beta here, we know that the force going up the slope has to be what we're concerned with. And so actually, because we're talking about acceleration, I probably should have just gone with g sine theta. Well, you could say force and then do forces then divide by m, but that's just making life hard for ourselves. We might as well just go for g sine theta. That's the acceleration down the slope, as it were, due to gravity. And so therefore, the force up the slope is going to be, do you know what? Seeing that they've given us the force, we might as well go for mg sine theta. There we go. And so the force up the slope, that's going to be F cos beta. Oh, stop writing theta, man. There we go. Therefore, resultant force is equal to F cos beta minus mg sine alpha. And so therefore, if F is equal to ma, then therefore we can just divide by m for the whole thing. So that ends up being, this just ends up being g sine theta like we said just now, but then this ends up being F over m cos beta. So it looks like our answer is gonna be B. It's gonna be B. 19, weight of a uniform bar. W pulling down like that. And there's our theta. And this is going to be to do with moments, so therefore we should probably be looking at this. Okay, so we're told that it's, so that should be in the middle, but we're not too fussed about that. That's W. The tension is 4W. Okay, so this is about moments, of course. So we're looking for clockwise moments equals anti-clockwise moments. So clockwise, that's going to be, well, let's just say that's 1W. That's that, plus 2W because it's at the end, so I haven't drawn it well, but that should be twice as far away from the pivot there. And then that's going to be equal to, well, just 1, because again, it's just the distance of 1. It's just arbitrary, isn't it? It's just half the length of the rod. You could use 1 and 0.5 if you wanted to. So that's 1 times, so it's going to be 4W, and then it's going to be cos theta, because we're concerned with the components of the tension that is perpendicular to the distance. So there we go. So that's going to be 3W equals 4W cos theta. So therefore, W's cancel. Cos theta is equal to 3/4 inverse cos. And so therefore, theta is equal to 41 degrees. So the answer is A. 20, classic projectile motion. It's going like that. And we have our initial velocity there is u. And we have theta. The range is d, so we're just being asked, guaranteed. There we go, classic question. A second projectile is fired with a velocity 2u at the same angle. What is the range of this projectile? Okay, so we know that the horizontal speed is going to be u cos theta. Vertical speed, upwards anyway, to begin, vertical initial velocity is going to be u sine theta. So very quickly, how do we go about looking at SUVAT? Well, we know that A is minus 9.8. We're going to be looking at time because that's going to come into our horizontal distance equation in a minute. V, we don't care about that. Well, we might do. I tell you what, let's go to there, okay? Let's go to the apex. So that's fine. I'm going to say V is 0. S, we don't care about that. Okay, so u is u sine theta. Okay, so what do we know? We're going to use v equals u plus at. So v equals u plus at. So t is equal to v minus u over a. This just ends up being 0, so it just ends up being that. So a is the same for both, so therefore we can say the time in the air is proportional to u. Fair enough. If we look at horizontal then, so horizontal, distance equals speed times time, because speed equals distance over time. Different v in this case, of course. So therefore, if u is doubled, that has 2 effects. So twice as long in the air and twice or double initial horizontal velocity. So therefore, both of these are multiplied by 2. Therefore, the distance should go up by a factor of 4. So I think the answer is D. 21, a particle traveling horizontally, constant acceleration, vertical acceleration. Okay. Oh, okay. So let's just say that it's going down like that, shall we? So its horizontal speed is 1 times 10 to the 7. I'm just looking for its horizontal distance, so that's okay. Okay, well, this is really easy, actually. This is just SUVAT. That's fine. So we just want to know how far, we want to know how far down it's gone. How far across it's gone, rather, when it's gone down a certain distance. That's fine. Easy peasy. So all we have to do is use SUVAT again. So S is going to be 0.08. U is 0 because we're talking about vertical. So therefore, its initial speed downwards is 0. It is moving horizontally, but to begin with, it's not moving vertically. V we don't care about. A is, I nearly wrote down 9.8, but that's not the case here. It is 4 times 10 to the 14 meters per second squared. Good grief, that's a big acceleration. And then time, well, that's what we want to find out. So S equals ut plus half at squared. And classically, ut disappears. So therefore, I'm going to say t, rearranging it quickly, is equal to 2s, root of 2s over a. And so that's going to be equal to 2 times 0.08 divided by this crazy acceleration. And that gives us 2 times 10 to the minus 8 seconds. Cool. And then all we have to do is go for horizontal. So very, very classic question. It could be a ball off a cliff. Just happens to be a particle in a field here. So horizontal, V equals D over T. So therefore, distance is equal to bt, just like the previous question. So it's going to be our crazy fast speed times our very short time. And so I think that that gives us 2 times 10 to the minus 1. And so that's going to be just 0.2 meters. So I think the answer is A. 22, object is thrown upwards. The object reaches its maximum height with t equals t, reaches terminal speed on the way down. Okay, the magnitude of the object's acceleration is A. Which graph shows the variation of A with t? Okay, so A is going to be negative, of course. Oh, okay, so it is downwards. Right. So when does A equals G? Okay, so it's not going to be A because we know it's constantly accelerating from the time that it's left the person's hand. It reaches its terminal speed on the way down. What? Reaches its maximum height. Yes, it's going to be that, isn't it? It's going to be because, but if it reaches its terminal speed on the way, it's terminal speed on the way down. But we don't care about what happens after it's reached its apex. Right. Okay. This is what I don't get. So at time t, or time 0, sorry, A must be equal to minus g, or just g, because it's accelerating downwards. So no, because its acceleration is going to be slower than that. But it's got to end up 0. A is going to be less than G. No, what am I chatting? Of course it's going to be greater than G. Yes, of course. What am I thinking? So you throw a ball upwards and A would be G if no air resistance. Therefore, A is greater than G if air resistance also pushing downwards. So we have gravity and air resistance pushing downwards. So therefore it has to be greater than G to begin with. And so what do we know then at time t? So that's, I got it now. So at the top, at apex, V is 0. Therefore, air resistance is also 0. Therefore, only acceleration due to gravity. Therefore, A equals G then. So yes, that is our correct answer. 23, man has a mass of 75 kilos, stands on a scale that accelerates upwards. What? Okay, so, and then this accelerates upwards at 2.6 meters per second squared. What is the reading on the scales during the acceleration? Easy peasy. It might look a bit bizarre, but it's just the same as your tension in a cable. And they've even given it in newtons, which is really nice. We don't have to convert it back to kilograms. So force is going to be equal to mg plus ma. It's as simple as that. If he was stationary or traveling upwards at a constant speed, then it would just be mg. But of course, it's going to be greater by ma. That's the extra force needed to accelerate it upwards. So easy peasy. So just 75. I'm going to factorize as well. 9.8 plus 2.6, and that gives us 930 newtons. So I think the answer is D. 24, average force of 42 kilonewtons acts on the air passing through a jet engine. The force causes the speed of the air to increase by 540. Oh man, not one of these again. So delta V is equal to 540. Now, what mass of air passes through the engine in 1 minute? Are we talking about energy or momentum? In this case, we're talking about momentum because we've been given a change in velocity. There is another question that was in the AS papers for this year, actually, that was really tricky. That initially looked like a momentum question, but actually it was to do with energy, how much energy was supplied to water passing through a pump. Right, so hopefully you remember that F is equal to Well, let's start from basics. So F is equal to rate of change in momentum. Okay, so because we have a change in velocity, therefore we're going to say that that is the same thing as m over t times delta v. We're going to split that up. And so therefore we can say that m over t, that's the rate of mass going through, is equal to the force divided by our change in velocity. So there's going to be that 4.2 times 10 to the 4 divided by 540. And then if we're just being asked to find out how much mass goes through in 1 minute, we can just say that that's 60. So we can just multiply that by 60. And I'm going to cancel a power of 10 there just for good measure. And that ends up being something like 4,670 kilograms. So I think the answer is D. 25, uniform wire is stretched by a load F. Elastic strain energy is E. Okay, the load is increased from F to 2F. What is the increase in the elastic strain energy stored in the wire? Okay, well, if you think about this, so, you know, we got F. Oh, hang on a minute. The elastic strain energy stored in the wire is E. Oh, no, the force is increased. Yeah, that's fine. So we know that, let's have a think about force against extension. Let's just call that X. Why not? It could be delta L. Let's call it delta L, actually. And we go up like that. Area under the graph is the energy stored, of course. And so I can already see what the answer is, but let's just go through it real quick. So we know that energy stored is equal to half FL, half F delta L. And so therefore, if F is doubled, then so is L and delta L rather. And so that means that the whole thing goes up by times by 4. Of course, we could have the equation half K delta L squared if you want one that just has one variable in. And again, you can see multiply delta L by 2 twice, that ends up being times by 4. So I think the answer is D. They caught me out. No, it's looking for the increase, isn't it? Therefore, going from E to 4E, therefore difference in energy is 3E. I got caught out. Bad me. Russian. Everybody's Russian. Okay, sticking with springs, or elastic stuff anyway. Okay, what's the average power developed by the spring as it returns to its original length? What the heck? Okay, average power, so energy is equal to, rather power is energy divided by time. And, well, this should be fairly easy because we know that we're talking about, we can't go with FV here, of course, we've got no V. But the energy, like we just saw, is equal to half K delta L squared. And so divide that by T. So this just ends up being a 2 on the bottom. Is that actually, is it just that easy? I think it is. I think the answer is C. Yeah, that's nice and easy. 27, 12 ohm resistor connected. I'm going to have to draw this. Okay, EMF. So that, and then we have, oh, okay. No, it's just internal resistance. Yeah, easy, I think. Whatever, let's draw it anyway. Okay, so EMF is equal to V plus IR. Whoops, got the wrong R. Silly me. And we know this is 2 volts. We know this is 4 ohms. And yeah, we're going to need the current. I mean, it's actually quite a bit easier than this. Let's be honest. It's just a ratio of voltages. We don't even have to think about the thingy, about the current. So it's just a potential divider. I mean, that's what internal resistance is. It's just 2 resistors in series, essentially. And so therefore we can just say the PD across the resistor divided by the total PD, or the EMF. Let's put EMF. Let's leave it as V total. Let's put brackets EMF. Is equal to the resistance of the resistor divided by the total resistance. So that should actually be fairly easy. So I'm just going to multiply that by V total. So therefore V is equal to resistance of the resistor divided by total resistance, which is 16, times by 2 volts. And you can ballpark this one as well, let's be honest. So it's just 3/4 of 2. So it's just going to be 1.5. So I think the answer is D. 28, small mass placed at P. Oh yeah, circular motion. I keep forgetting that this turns up in this paper. We've had no circular motion or SHM in this paper. How weird. Yes, anyway, okay. We've only got a few questions left. Turntable rotates clockwise. What have you just been asked? What is the direction of the frictional force on the mass? Oh, come on. Good grief. Frictional force, just like any centripetal force, always goes towards the center. So that's downwards like that. That's from P to O. That's supposed to be an O. And so that ends up being Easy peasy. Just trying to catch you out by wording it weirdly. 29, particle, blah, 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 blah. What is the kinetic energy of the particle? This question's come up in loads and loads of papers in the past. Do you know what I always do in my head in? That's better. Okay, kinetic energy of the particle. We know that speed is just distance over time. So that's 2 pi r over t being the time period. And of course, we can just say that frequency is 1 over time. So that just ends up being 2 pi fr. That's a classic thing that we see quite often. And kinetic energy is equal to half mv squared. So popping v squared in there, we end up with half times m times 2 pi fr all squared. Or in other words, half times m times 4 pi squared f squared r squared 2m f squared pi squared blah 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 blah. It looks like B is our only option. 30. Body is in simple harmonic motion. Finally, we have an amplitude of 0.6 meters and a period of 2 pi seconds. I'm going to put seconds there. What is its speed when its displacement is 0.2 meters? Easy. We're just going to get our equation for this. It's plus or minus. We don't care about that too much, but it is omega times the square root of a squared minus x squared, or in other words, 2 pi f. We could say 2 pi f. Let's write it out, fine. Or it's very unusual for us to use this equation. I like it though. The whole thing anyway. Usually we just deal with maximum. And so that's 2 pi over t times by a squared minus x squared. So that's just going to be 0.6 squared, take away 0.2 squared. And so if this is 2 pi, then that cancels nicely. And so we just end up with the square root of 0.36 take away 0.04. And so this ends up being the square root of 0.32. Can't do that in my head. And they do have 0.32 there to throw you off, but no, we want the square root of that. And it ends up being 0.57 meters per second. So I reckon it's B. 31, mass suspended from a spring, oscillates, it extends by distance x, m is displaced vertically, and when released, okay, fine. Oh my days, the spring extends by a distance x over 2. Okay, so if delta L is halved for same mass and force, that means K is double. Fair enough, the spring constant is doubled, the stiffness is doubled. M is again displaced vertically and released, right, so there we go. So we're just going to get our time period equation, so it's 2 pi root m over K. Same mass, etc. We could calculate it, no we can't actually because it's just m, so this is just a proportionality dealio. Okay, so that means that T is proportional to 1 over root K. And so if K is doubled, then that means that this bottom bit multiplies by root 2. And so that means the whole thing divides by root 2. And therefore, so does T. So we're looking for, yeah, B. That's our answer. Finally, 32. We've seen this question so many times before, right? So both are taken, we have a pendulum and a spring. You should remember that, well, let's just look at our equations, shall we? So for a pendulum and for a spring, there is no G in the spring equation. So it doesn't matter where you take a spring, it's always going to have the same time period as long as the mass is the same and the spring is the same. That's why they use springs in space to measure the mass of astronauts, because obviously they can't use a weighing scale up there. So therefore, we know that the answer, wait a minute. Oh no, spring system. Yeah, I mean, you can see that they've given us 2 with the same time period. So it can't be A and it can't be D. So then we're just looking at the period of the time pendulum. So let's have a look. G halves. So that means this multiplies by 2. That means that the whole thing multiplies by root 2. So it looks like our answer is C. So there we go. Hope you found it helpful. Don't forget to leave a like and a comment and click on the card, which will take you to the playlist for all of the papers, including the paper 2 for 2024 too. And I'll see you next time.